Okay, so my non-dimensionalized, nonlinear Poisson-Boltzmann equation now says that the local Laplacian is basically given by a sum of ion concentrations multiplied by the valence, but also with this correction factor for the fact that if the potential is different from 0, there is no longer net electron neutrality. Now, this equation, while simpler, still doesn't really make any sense to me. And so I would like to discuss some simplifications. The first one, let's discuss how this simplifies for what I'll call a symmetric electrolyte. And by symmetric electrolyte, I simply mean that I have two different species. One is positive and one is negative. The valence of the positive one is the opposite of the valence of the negative one. And the concentration of the positive species is equal to the concentration of the negative species. So for example, if I had a 10 millimolar sodium chloride solution, that's symmetric. If I had a 5 millimolar magnesium sulfate solution, that's symmetric. What is really nice about that case is I could take all these z sub i's and just call them z, and have that be the absolute value of the valence. And when I do this sum, now I'm going to have two different concentrations which are the same. And what I'm going to get is a negative exponential plus a positive exponential. I'm going to take the average of the negative and positive exponential, and I'm going to divide it by 2. What happens when I take a negative exponential and I'm going to take the difference between the positive exponential and the negative exponential, and I'm going to divide that by 2. Right. I get a hyperbolic sign. Right. So in this case, my expression that has sum of c times z times exponential minus zi times phi basically just becomes sinh of z phi. And the only difference is that I have this sum then of these concentrations on these species, except I already know that the sum of 1/2 sum of ci zi squared is equal to 1 because of the way I non-dimensionalize this. So all this stuff goes away. I basically end up just getting the sum and difference of exponentials. And when I do this, I get this expression. And so by assuming that it's symmetric, I took this sum, which tends to make things awkward. I was able to recast this as the sum and difference of positive and negative exponentials. And now I have this hyperbolic sign. I can approximate this further by saying, what if phi star is less than 1 everywhere? Right? What if I have a wall where the surface potential is 1 millivolt? It's very small as compared to 25 millivolts. If this argument is small, what approximation can I make about hyperbolic sign? Like if x is really small, how can I approximate sinh x? It's just with the argument, right? So in that case, now I have 1 over z times phi star. And now I get a very simple expression. So again, in general, my Poisson-Boltzmann lets me sum up the charges on the right-hand side, sum of c times z times this correction factor associated with the local potential. In a number of cases, I can simplify the structure of the equation. For example, with a symmetric electrolyte, I can now write this in terms of a hyperbolic sine. This is still nonlinear, but it can be written in a compact form. And I can linearize it if I assume that phi star is much less than 1 everywhere, in which case I get this expression. My shoulder has totally come back. All right, well, let's go back to our original problem, right? We have a wall. I've said that this wall has a value phi is equal to phi naught at the wall. If I start with the very simplest case, if I assume that phi naught star is much less than 1, then I can consider solutions of this linearized form of the equation. And if I write that expression in one dimension, I get this. Now, what are the solutions of this? Okay, get sine of cosine, or yeah, so I can combine it together in a bunch of different ways, right? I can have sines or cosines, sinus, coshas, exponentials with positive and negative exponents. Right? Well, I said that by definition, that the potential was going to be 0 by definition in the bulk. And that basically rejects sinh and cosh and sine and cosine and e to a positive exponent. It really only allows a solution where it's exponential to a negative component. So the only solution of this that satisfies the boundary conditions is this one. Or rewriting it in dimensional form, so this now is super easy. Now, admittedly, this only works if I assume that lambda naught star is much, much less than 1. If we assume that lambda naught star is much, much less than 1, we can see from the form of this equation that, sorry, not lambda. We assume that phi naught star is much, much less than 1. From the form of this equation, if phi naught star is much, much less than 1, this also will be much, much less than 1 everywhere, which is technically what's required to make this form of the equation correct. And now in this simplified case, I can say that this potential just exponentially decays away from the wall with a characteristic length that's lambda d. This again comes back to why I included the 2 in when I defined lambda d. If I left the 2 out, I would have had I believe, a square root of 2 extra constant in this equation, which I could have left in. But the convention is to put that 2 in the definition of lambda d, so that that lambda d becomes a definition for the characteristic exponential decay in space of the potential at the wall. So if I now make a graph of phi as a function of space, now I can draw this distribution very simply. I have an exponential decay from a maximum potential at the wall down to a value of 0 at infinity. The characteristic length over which that decays is lambda d, and lambda d is a property of the bulk solution. It's not a property of anything going on at the wall. It's a property of a bulk solution. And it's given by epsilon RT times 2 F squared IC. So what does this tell me? If I have a really, really high concentration of ions, if I keep increasing the concentration of ions, does my Debye length get shorter or longer? Shorter. Lots and lots of ions, my ionic strength goes up. That means that my lambda d goes down. Right? So that means that if I take a surface that has a potential and I stick it in an electrolyte solution, the immediate thing that happens is the ions around it go to the wall and shield that charge. They shield that charge over some finite distance. And if you have more ions around, the solution is much more efficient at shielding that potential. It shields it over a shorter distance. If I increase my ionic strength by a factor of 10, I'm going to make this distance smaller by a factor of 3, or square root of 10. If I increase the temperature, what happens to lambda d? It goes up. Why? What's the physical process by which an increase in T should make the thickness of the electrical double layer bigger? So it's definitely true that my equilibrium relation has T in the denominator. I have e to the minus e over RT. And if I make T bigger, that exponential is lower. So I agree with that. But by what transport process do I think that if I increase T, I'm going to have it be thicker? Diffusion, right? This whole thing, this is all happening, this potential distribution is all happening because every ion in the system has some decisions to make. If I have a negatively charged wall, if I have a negative ion here and a positive ion here, this positive ion is attracted to the wall, but as it's attracted to the wall, the concentration of positive ions gets big near the wall, and therefore there's a diffusive term away. That diffusive term gets bigger when the kinetic energy of the system gets bigger. Similarly, this negative ion wants to move away from the wall, but as it's doing that, it's depleting this region, and again, there's a diffusive flux bringing it back. At equilibrium, these are all perfectly balanced. You can see in here the relation between these different things. The temperature tells you how much the diffusion balances out the Coulomb forces that are pulling these ions closer to and farther from the wall. And this ionic strength basically tells you, okay, what is the density of ions you have to work with? Lots and lots of ions will shield this potential faster than if you have small amounts of ions. So now the picture we have, if I have a wall, if I assume that this wall is negatively charged, is that there's a cloud of positively charged ions, which we'll call counter ions. That is attracted to the wall. I have positive ions everywhere, but in particular I have a high density near the wall. That's because of that attraction. They're not all jammed up against the wall. In fact, there's a finite distance over which these ions are piling up, which is lambda d. Similarly, the ions that have the same charge as the wall, what we will call co-ions, in the bulk are at about the same concentration as the positive ions. But if I look near the wall, I'm going to find very, very few of them. If I look at the distribution of the potential in this linearized solution limit, I see a nice exponential decay. And in this linear limit, I also see an exponential distribution of the co-ions and counter ions as well. So if I graph the concentration of ions as a function of y, and I say that this is the concentration at infinity, and I assume I have a symmetric electrolyte, For my negative wall, my negative ions will have the bulk concentration until they get close to the wall, in which case that concentration will go down because there's an electrostatic repulsion. My positive ions will have the bulk concentration until they get close to the wall, at which point that electrostatic term will increase them. In the linearized limit, this change that you see, the increase in the counter ions, is perfectly balancing the reduction in the co-ions. And so if I were to calculate the total concentration of all ions in the system, it doesn't change near the wall. I just replace my negative ions with positive ions near the wall in the linearized limit.